Okay, so circular motion. This has, related to rotation, but it's not about rotating objects. It's about objects that trace a circle. Their motion traces the circumference of a circle. And so you're going to hear, some of those circumference, radius, 2 pi r, that's coming, okay? And so to get this started, most of your problems are considered uniform. I can't write today. Uniform circular motion. Or you may see it abbreviated in some books or review books or videos as UCM. And so uniform circular motion, unless they make a change, remember AP always loves to make a change there at the end, it has a constant speed. So constant speed, yes, but not a constant velocity. Now, previously, maybe we were a little loose and we said, oh, it's both. Constant speed, constant velocity, same thing. For an object moving in a straight line, that can be true. They can both be the same thing. But when an object, whatever it is, so maybe I take a ball, maybe there's a string, maybe it's going to have a tangent velocity. VT is a tangent velocity. So it has a velocity vector in one direction. It ends up being tangent to the circular path that the ball is going to make. So there's a first stipulation. Usually when an object is moving in a linear fashion, we don't say tangent velocity. Technically it is, it's still tangent to the linear path, but we just say velocity or speed. But here it's tangent to the circle. Okay, so it's a little more specific. And why do we make that stipulation? Well, later on, we'll talk about angular velocity, and it's related but different. And so what if it goes around in a circle at a constant speed? It's not constant velocity. Why? You got to go back to August. What's the difference between speed and velocity? One's scalar, one's vector, right? So what's the difference between scalar and vector? One has direction. Now, which one has direction? Velocity includes direction, right? So they both have a magnitude, but velocity cares about direction. And so for an object moving in a circle, why do we not say it has a constant velocity? What's happening in a few seconds, it's going to be here and have a tangent velocity in a new direction. And so why not a constant velocity? Direction changes in circular motion. Okay, but it could, hook it up to a motor type maybe, or do your best, as a human, right? You could have circular speed, constant speed, just not constant velocity. And so is it accelerating? If the number never changes, does it have acceleration? Well, if we go back, define acceleration. Is it a change in speed over time or a change in velocity over time? It's a change in velocity over time. Well, the velocity is changing because the direction's changing. Now, I can't show you that numerically if the magnitude never changes. So we're going to do a little vector addition. Actually, it's going to be vector subtraction. So hopefully you remember vectors. Whenever you put one vector together with another, you've got tip to tail, and then we've got a resultant. Y'all remember those words? Okay. And so I can't show you mathematically because if we plugged in, 5 minus 5 divided by, 10 seconds or whatever, you're going to be like, no, it's not accelerating. The number never changes. That would be true, But because the direction's changing, yes, there is an acceleration, okay? Because direction changes. And so let's do a little vector addition. I'm going to use those two places that I've already identified. Now, I know we're in a digital age and probably some of you don't even own a watch. You've always maybe depended on cell phone or, smart watch. Maybe it's digital. The clocks in the hall at the main campus have transitioned to all digital clocks. Back in the day, we had an analog clock. And on purpose, I keep an analog clock, and I'm pointing at my old school clock at the board, right? So I have an analog clock. If we were to put this picture on top of it, if I say that we start at the top of the circle, isn't this like a 12 o'clock position? So I'm going to kind of use some watch or clock times, but this isn't for timing. It's just as a position. So if I say that it starts at 12 o'clock and ends at, this would be 9 o'clock, and no, it doesn't matter if it's AM or PM. These are positions. We're not really using this for time. So don't start thinking I'm going to put in 3 hours here, okay? It goes from 12 o'clock to 9 o'clock. We're going to take these two vectors and do vector addition. And so keep that going. Acceleration equals a change in velocity over time. Well, time is scalar. And so time doesn't affect the acceleration's direction, only the magnitude. And so we're going to just say acceleration is proportional to your change in v in terms of direction. Let me write that out. Direction. And so whatever direction we get from our vector addition with velocity vectors, so will be the direction the object is accelerating when it comes to 12 o'clock to 9 o'clock. Everybody good what we're doing? That fishy alpha symbol is talking about being proportional, okay? Okay, and so change in velocity. Maybe I slide over a little. So change in velocity, delta, change in is always final minus initial. Well, what's your final velocity vector? Not magnitude, not number, but direction. Well, if we look at our picture, it's down. So I've got down minus my initial velocity at 12 o'clock, I designated as to the left. Everybody good so far? We haven't been thinking physics for a while, so please shoot that hand up if you're like, wait, what did you just do? Let me know, because you're probably not the only one with that question. And so this is what we're going to do our tip to tail. But maybe you remember it's called vector addition, which is a little bit different than vector subtraction. And so now looking at these, to have addition, you would take VF plus a negative VI. So this is like vector subtraction. But to follow the whole tip to tail, that's vector addition. And so how does it differ? You just add the inverse. Add the opposite direction of VI. And so VF stays the same. It would be down plus, what's the negative of left? What's the opposite of left? And everybody says, to the right. Okay, and so this is your negative VI. These are the two vectors that we're going to put tip to tail and find the resultant, which is going to be our change in velocity. That's going to be our resultant. Okay. And so tip to tail. It doesn't matter which one we start with. So, but I'm just going to go in order here. So I've got down, and then at the tip of the first, I put the tail of the second. And so this is my VF. This is my negative VI. And where's that resultant? Who remembers? Do I finish the cycle? How do I draw in the resultant? Don't finish the cycle, right? So if we think about that, I use treasure hunt for vector addition, right? And so you can either go down and right to the treasure, or put it together. What's down and right all together? It's from start to finish. That's supposed to be a straight line. And so this is your resultant, start to finish. And because of this VF plus a negative VI, that would be your change in velocity's direction. And remember, it's proportional to your acceleration. So once again, we have a constant speed, but direction is changing. And so it's also the direction of your acceleration. Is everybody good with the tip to tail and resultant? So let me go put this acceleration vector. I'm drawing arrows. I'm labeling them with V's and A's. This is not a force diagram, right? Force diagrams only have forces. Don't worry, that's coming. But I'm going to take this southeast, if you will, vector for my resultant, for my change in velocity, for my acceleration, and I'm going to go put it in my original picture. Now, where do we put it? Well, usually when you pick 2 points that are far apart, you put it in the middle, middle-ish. And so from 12 o'clock to 9 o'clock, you have an acceleration southeast, down and right. Let's do one more, and then we'll come to a conclusion, okay? We could do example after example, pick all the times on the clock, do the half hours, but hopefully after a couple, maybe we see a connection. So now what if, I'm going to change colors, we'll draw a new picture. No, I'll keep the same picture. Sorry. Purple. What if we do 6 o'clock? We'll keep with that same counterclockwise direction. We'll keep that the same. Counterclockwise, clockwise. Again, old-fashioned analog clock comes to the rescue. And so here, we'll call this our initial. And then we'll call maybe 3 o'clock our final. So let's do the same tip to tail, vector subtraction, transition into vector addition, and see that from 6 to 3 o'clock, what direction are we accelerating? And so maybe I come down here. Delta V, we've got VF minus VI. Again, for vector addition, we're going to call that plus a negative VI. And so with our second example, final is 3 o'clock. 3 o'clock. Initial is our 6 o'clock. And so final is up plus negative right. What is the same thing as negative right? Left. Okay. And this is what we're going to do, tip to tail. Tip to tail. And so we've got, nope, up, and then we've got to the left, tip to tail, up and left. Resultant is what direction? Start to finish. And notice up and left is the same thing as northwest, right? Or correct? Northwest, correct? And so again, that's also the direction of your acceleration, because the time doesn't have any direction. The direction of your acceleration is based on whatever direction the velocity is changing. And so now I'm going to go up to that 3 o'clock and 6 o'clock. And again, those are pretty far apart considering some other examples. I could have picked 6 and 5 o'clock, right? But to me, those angles are harder to draw by hand. Up, down, left, right is easier to draw by hand. So between, kind of midway between 6 and 3 o'clock, I'm going to put a northwest vector, and that's the direction that it's accelerating. And we could keep going. I don't mind doing one more. Do we have any conclusions about the acceleration of an object moving at a constant speed in a circular motion? Let's do one more. Let's do one more. I'm running out of colors, so bear with me. Maybe I start a new picture, but same concept. And so what if we do 3 o'clock? We'll keep same counterclockwise direction, and maybe we go to 12 o'clock. We kind of end where we started. And we got, notice the dashed line is just the path. The ball can't be in two places at once. So we are looking at two different times in real time, right? In real life, it can't be in both places. And I haven't even put, how does the ball get there? There's going to be a string. You can do a ball on a string, okay? And so now if we do initial at 3 o'clock, final at 12 o'clock, let's go through that vector addition again. So delta V is final minus initial, but we're going to turn it into vector addition. And so final is to the left, plus what's a negative up? Down, and tip to tail those two. It doesn't matter which one goes first. I usually just go in order. And technically, and I don't have a ruler here, but technically, these are all at a constant magnitude, constant length, okay? The VI and VF, because our object is moving around at a constant speed. And so there's my tip to tail. Where's the resultant? Resultant is start to finish. And so from 3 o'clock to 12 o'clock, we get southwest. I'm going to go put that on the original picture so we see all three accelerations at once. So from 3 o'clock to 12 o'clock, and so just to highlight what we're looking at, have we got any conclusions? What direction is your object accelerating when it travels in circular motion? Notice we can't say northeast, southwest. We can't say that because that's not true all the time. Any guesses how you would define centripetal acceleration's direction? All these arrows point where? And by the way, if you take a little, educated guess, if we did 9 o'clock to 6 o'clock, what direction would it accelerate? Are you noticing a pattern? It would accelerate this way. If we were to do the tip to tail again, what do they all have in common? They're pointing towards the center, okay? So there's our big idea for circular motion. Yes, an object traveling at constant speed around in a circle is still accelerating. It's still accelerating towards the center of the circle. And by the way, that's defining our positive direction, okay? Put that in a different highlight. Center seeking, centripetal acceleration is a center seeking, okay? Centripetal means center. And so sliding on down, oops, centripetal acceleration means center seeking. Okay, so towards the center is the positive direction. What would be the negative direction? Any guesses what the negative direction would be? Out, away from the center, opposing is what I usually say, 180 degrees from center seeking, okay? And so away from the center would be considered the negative direction. Now, we'll come to the forces approach here in a second, okay? I want to get the centripetal acceleration equation that we're going to use, and then we'll start bringing in forces. And so that is our positive direction towards the center. It's not any forward being positive anymore. So that's what's unique about circular motion. Good deal? Again, all those change in velocities, all the resultants that we got pointed towards the center. Okay, so let's get our acceleration, centripetal acceleration equation. Now, lucky for you, this one is on the formula chart. So find a formula chart. So it's there, but I'm going to show you how it comes to be. And so on the formula, hold on. On the formula chart, I believe, do they have a little subscript C, AC? Look at the 6th or 7th equation down. Don't really know what number of equation it is. Do they have AC? Yes, excellent. It equals V squared over R. Now that V, I've been writing VT, it is a linear velocity. So I usually go on and say VT, just to make it special. It's not using an angular velocity. That has a different variable, actually. And it's not just any old velocity, it's a tangent velocity. And so that's the equation. It is on the formula chart, but how does it come to be? Because all we've done is direction. How do you get the magnitude? Now, there's a couple ways to do this. Okay, I'm going to show you the proportional way to get it, but there's a similar triangle approach. To me, that takes a little longer. Okay. And so bear with me. First, we're going to look at how does acceleration, well, how do you get that VT squared? What's up there? And so for the first part, A or 1 or whichever, let's look at how AC, centripetal acceleration, is proportional to VT squared. And so the first example I want to put down is let's take that ball on a string or whatever it is, moving around in a circle. We'll make it go around with a radius of 1r and a velocity of 1v. Okay. Now we're going to make a change, but before we do that, let's think about if it's going to go around in one complete circle, what distance does it travel? An object moving in a circle, what distance does it travel for one complete circle? 2 pi r. This would be the circumference. So we're going to start getting into circumference. And so it would be 2 pi r. And while we're there, let me go in and give you another unique to circular motion term. What about the time it takes for one complete circle? Well, this is known as period. Okay, period is a capital T. Okay, and that I think is on the formula chart because I pointed it out before. It's not tension, it's period. And so what is period? It's the time an object takes to make one complete circle. Everybody good? Okay, and so if I've got a radius of factor 1 And the velocity is a factor of 1. Well, let's take a look at an equation that kind of puts all those together. That tangent speed would be the distance it travels, 2 pi r, divided by the time it travels, period. So this is a very common equation, not on the formula chart directly. You'll see the spirit of it later, okay, on the formula chart with angular velocity. But this is the distance of one circle divided by the time of one circle, and we get a tangent. Notice I'm saying the word speed here. Yeah. But speed doesn't really get a variable on its own, right? And so I'm still writing a v, but it's the speed of it. Okay, I guess to make it correct, we can take off that t. Oops. So note to self, this is really the speed of it. So this is getting into finding the magnitude. And so now, if we know it goes 1v, 1r, how much time does this object take to make it around in a circle? If v is a factor of 1, r is a factor of 1. Now 2 pi, hopefully you know 2 pi means one complete circle, right? That's going to be the same no matter what changes I make. So kind of just ignore that. Look at how v and r and t. If v is 1 and r is 1, then t is factor of 1, okay? And so this would take 1t. One factor of whatever period it takes. Everybody good? So these are proportions, not exact numbers. What if we do the same radius, but now double the speed? So now same radius, but we double the speed. And so I'm going to try and draw my circle about the same. So we still have a factor of 1r, but now it's moving 2v. Well, if I'm moving faster, twice as fast, and I'm making the same 2 pi r, how much time is it going to take to make one complete circle? You can use the formula in proportions, or you can kind of do a little intuition. If you're going twice as fast, making the same circumference, same distance, how much time is it going to take? More or less? Less time. Now, what factor of? Well, instead of 1t, it would actually be half the t. It's going to take half the time. Yes? Okay, hold that thought. Let's triple the original speed. Same radius. And so still 1r. 1, 2, 3. Maybe now we triple the speed. What period would it take to make that one complete circle? 1/3 t. Okay. Okay, and so how is this going to get us the v squared? Well, let's take a look. Again, acceleration is proportional to your change in v divided by that change in time, right? And so notice when our change in v, let's say, just doubled, our time went down by 2. Well, if I divide by 2, but also multiply by 2, what's going to happen to the acceleration? If the top doubles and the time denominator is half whatever the original was, that's going to equate to what magnitude of acceleration? 2 divided by 1/2? We get 4 times the acceleration. What if we do it with the 3? And so if you go from original v to 3v, and I have a triple v, sorry, I wrote an X there, I meant to write a v up there. and we have 1/3 of the time, then what kind of acceleration do we get? 3 divided by 1/3? 9 times the acceleration. And so how do we get this acceleration is proportional to v squared? Well, whatever v does, if you just square that, so if it doubles, double squared is 4 times the acceleration. Because what's not written in the equation is the time piece, okay? But the time does change when you change the velocity, the speed. Does this make sense? And so that's how we get that acceleration, centripetal acceleration, is proportional to v squared. Okay, so hopefully that explains why the numerator is v squared. That was all under constant radius. Well, now let's go back to the original and change the radius, but keep the speed the same. Again, a good scientist only makes one change at a time. And so last piece here, and then we'll get into forces. And so back to the original. So now we're going to show how acceleration varies with radius. Now I'm going to go on and be more correct here. It's an inverse radius, just FYI. And so back to the original, 1 radius, 1 v, and we know it's going to take 1 t, because again, that circumference over time equals your speed. Well, now let's have a constant speed, but let's double the radius. And so our next picture, still 1v. I'm going to do my best here. Not drawn to scale, but maybe we double the radius. And so again, in your mind, you're thinking, well, the magnitude, that linear speed, if you will, it's still tangent, but magnitude, linear speed, is always going to be that circumference over period. Well, now I have a constant speed. And so if your radius goes by 2, if your radius doubles, what does the period have to do if you're traveling at the same speed in order to keep the equality? Period has to double as well, right? To equal that 1v. And again, I know you're like, well, what about 2 pi? We're never making changes to 2 pi. Notice we're doing 1 complete circle every time. So you could, play the AP game and put some other kind of constant in there. It's never going to change. Now, I will be honest, sometimes maybe we'll only travel half of a circle. But right now in this example, I'm always going 1 complete circle. Everybody good there? We'll go back to magnitude of acceleration. It depends on your change in velocity divided by that change in time. Well, there is no change in our tangent velocity, tangent speed, and so no change up top. But what happens when your time doubles? Well, it's a denominator. So what does your acceleration do? It's going to decrease by what factor? You would get half the acceleration compared to before. Before, I guess I should have said that we would have 1a, right? 1a, because 1 change in v, 1t. Before we made any changes, maybe the acceleration was 1a, whatever it is. But now that I've doubled the radius, that's going to double the time it takes to make it around. And that's going to make it half the acceleration. Well, hopefully you're catching on. Now, let's triple. Again, not drawn to scale, because it might look the same. Just work with me here. So same 1v, but now it's 3 times the radius. Keep that circumference over period. Again, v equals that 2 pi r over period. Your velocity value, magnitude, speed is going to be the same. But now I have 3 times the radius, so it's going to take the object 3 times as long to make it around. And when we go back to that original defining equation for acceleration, there's no change in the speed in this example, but now we have 3t. So what kind of acceleration will we have at a triple radius? A third. And so you kind of put all that together. So when you change the radius, the period can still change, but what also changes is that acceleration. And so this shows us that acceleration, and again with circles, it's a centripetal acceleration, is proportional to the inverse radius. Okay? And again, there's a similar triangle approach that you can use to get the equation, but put those two relationships together, and this is the equation for centripetal acceleration. Everybody good there? Now, I've been talking about a ball on a string, and it would be helpful if I actually showed this. So hold on a second. Don't think, hold on. I used to have a little rocket man, so it's foam. That way, if I accidentally bonk you on the head, it didn't hurt. Okay, I don't know where my rocket man on a string is. Here, I've got a string. A lanyard is a string, yes. Now just ignore that it's 2. Okay, I'll keep it at a small angle so it's behaving as 1. How about that? And then I've got a small mass here. And so what we've been demonstrating is maybe a vertical circle. See this? Now let's answer this question. Because of blank force, this object moves in a circle. Yeah, I'm trying a constant speed. Now we know the acceleration is towards the center of the circle, right? But answer the question, what's the source of this circular motion? In other words, without this force, it would not move in a circle. And note, I am not touching the key. So don't say applied. Without this force, ignore that. Without this force, the key would not travel in a circle. Not centripetal. What's actually acting on the key? Gravity, check. And there's a string. Tension, okay? And so warning, warning, in this unit, we'll be using tension and we'll be using period. And so for those of you, AP included, watch out for your circular motion AP questions. If you see a capital T, don't just assume it's period or assume it's tension, look at context, okay? If it's T equals 60 N, that's 60 newtons, that's a tension. If it's 60 S, that's 60 seconds, that's a time, right? And so without gravity, yes, gravity still plays a role, but it's mainly the tension, okay? What happens if this string breaks? AP loves to cut strings. What if, it slips off my finger? 3, 2, 1. Oh, crud muffins. How did it find the 1 centimeter gap under the cabinet and slide underneath? Y'all remind me after y'all leave, I got to get the meter stick out and retrieve my key because I can't control the electricity and water in the room without that key. Okay, where's my rocket man? Rocket man is bigger. Anyway, goodbye key. But notice, did it continue moving in a circle? When it slipped off my finger, no more circle. Who was driving the key then? Only gravity. So did you notice the path? I should have told you to watch the path, right? It became a projectile, right? Okay. Now I won't let go of this one. So that's a vertical circle. Gravity and tension both play a role. Look, I'm even going to loop it, okay? Because this one will hurt if I let go. You can also take your ball and string and make a horizontal circle. Now these are harder to draw on paper, okay? You're looking at a three-dimensional circle. So you may see these drawn as ellipses or kind of done as a side view or a top view. If you were up above looking down on this circle, you would see a circle, right? And so this is a same ball on a string. Yes, gravity's still working on it, but is gravity in the direction of my horizontal circle? Gravity is a vertical force, right? Well, this is a horizontal circle. So the only forces causing this object to go in a circle should be horizontal forces. So now answer the question, who's responsible for this object going in a circle? Just tension now, okay? So don't start memorizing, oh, ball on a string, it's always tension and gravity. That's if it's a vertical circle, right? So what if it's not all about balls in a string? What if I go back over here and I trace a circle? I'm moving in a circular path because of who? Watch it. It's a horizontal circle. So the answer is not gravity. But because of this force, I can make a circle. Without this force, I would not make a circle. Can anyone guess what force is responsible for me walking in a circle? Whoop! Friction, right? Without friction, would I be able to make the turn? Note to self, on icy days when ice is on the road and you're driving in the car and you see a bend in the road, a curve in the road, it doesn't even have to be a full circle. What should you do? Even on a dry day, you should, but definitely on an icy day, you should. Slow down, because to make the circle, we do have limits, okay? And so coming up, there's these max speeds, minimum speeds. And so if I'm trying to go too fast, that's fine. Do you think I'm going to make this same tight, small radius circle? When you run, maybe you need a bigger radius, okay? Because I might drive off the road, okay? Objects don't want to travel in a circle. Objects want to travel in a, what is the key that is now under the cabinet? It didn't, when it slipped off my finger, it stopped moving in a circle. It wanted to go in a straight line. Now gravity was in the driver's seat, so it became a projectile. But if I did that same demo in outer space and it slipped off my finger, it wouldn't go down. Outer space, no gravity, it would just go off in a straight line. Yes? Now let's talk about, before I start drawing force diagrams and such, I just want to get this out of the way. Some of you are thinking, oh, Miss Zerhart, you haven't talked about centrifugal force. Centrifugal force, okay? Centrifugal force. When you drive that car in a circle, your body might slide into the door, right? And you feel, oh, there's something pushing me, right? Trying to leave out of the circle. Something's pushing me out of the circle. No, nothing's pushing you out of the circle. Just like that ball on a string, something's pulling you into the circle. Centripetal is center seeking. So what is that outward force that we tend to feel? It's something we've already learned. It's something called inertia. If you're in a car that's turning a circle, your body wants to travel out of the circle because that's the straight line direction. Hopefully there's a door there. Hopefully there's a seatbelt there to say, no, come back into the circle with me, okay? If there's no door and no buckle and no friction with the seat, then you're going out the door in a straight line because that's inertia. Objects in motion, traveling in a straight line at a constant speed, want to continue in motion traveling in a straight line at a constant speed unless there's an unbalanced force. So again, going back to Newton's first law. So anytime you feel that you want to say centrifugal, correct yourself. No, that's inertia. It's a tendency to keep going in a straight line. That's why you want to leave the circle, but there's some force bringing you into the circle. And if there's no friction with the road and you don't make adjustments, that car is going to go off the road in a straight line. Does that make sense? And I hope you never have to experience going off the road, but slow down. Question. So it's from a different frame of reference. And so we always take the inertial frame of reference, our object, right? And so we're not on the outside looking in. We're here at the object's kind of point of view, watching this all happen. So in AP physics, you're not going to encounter centrifugal force. You have to change a frame of reference, okay? So it's not wrong, but it's wrong for AP physics. I don't want you, getting confused. So just get centrifugal force out of your vocabulary for the AP Physics 1 exam. Okay, let's start doing some examples. And page 2, we've got some. So we're going to start with some basics. And so here, number 1, it says a jet plane traveling at 1980 kilometers per hour. Don't worry, we're not going to convert it. It's already converted. 525 meters per second, pulls out of a dive. So maybe this plane is diving towards the ground and they pull out and they make an arc of a radius 6 kilometers. What is the plane's acceleration in grams? Wait a second, what? It's a callback to that G-force or G's, right? We talked about pilots and astronauts. They got to be able to withstand, not black out, about 6 G's, okay? And so we're just going to find the acceleration and then divide by 9.8 or 10 to put it in. It's a factor of the acceleration due to gravity. So it's not grams. And so if you want a little picture, maybe here's your airplane. I'm not a good artist. Okay, so there's our elongated ball. So here's our airplane. Put some wings on it, I guess. Looks like a protozoan or something now. But it's going to pull out and make the arc, right? And so it doesn't matter if it's going to travel in a full circle or not, at least for this problem, because to get the acceleration, we just need the velocity. We're going to square it and divide by the radius and look at the 2 items given. So this is a level 1 type of problem. They already gave us the velocity, so plug and chug. Now 6 kilometers, you do need to know kilometers is how many meters? 1,000. So I'm going to say 6 either times 10 to the 3, or you could literally just say 6,000. And hopefully you can grab a calculator. Oh, they may not be charged. Hold on. I unplugged them all over break. I'll go for my solar here. So 525 squared divided by 6,000. I get 46 meters per second squared. Now, how many G's would that be? How many factors of gravity? So divide by 9.8 or 10. So this is 1 G. Divide it by 10 meters per second squared, and we get 4.6 G's. Okay. Which, if you've ever ridden the Titan the Titan at Six Flags, the circular portion of it, the corkscrew, I've read that that's 4.5 G's. Miss Earhart blacks out, so I would not make a good pilot. Okay. Okay. Cookie cutter, not too bad. What if 2? A 1,000 kilogram car, do we need to convert that? Who remembers the SI unit for mass? Is it gram or kilogram? To convert or not convert? So we converted kilometer to meter because meter is SI unit for a distance, but kilogram is the SI unit for mass. So don't convert this one, okay? And again, on the front of the formula chart, they give you some of your common units. Now they don't say it's SI units, but all of them are except Celsius. That's not the SI unit for temperature. But kilograms is good. So this is the mass of the car. It drives around a circular track. So kind of like me walking around in a circle. This is a horizontal. Okay. Radius 2 kilometers. Do we need to convert it? Yes. So I'm just going to go straight for 2,000 meters at a constant speed. Now they don't tell us what that speed is, but just wait for it. We know it's going to be constant. And then they say doing 1 lap, 1 complete circle per minute. How do you feel about minutes in SI units? What's our SI unit for time? Seconds. And so 1 minute would be 60 seconds. And if that's the time for 1 complete circle, what are they telling us there? The period. The time for 1 complete circle, whether it's a ball on a string or a car on a track, is going to be the period. What is the speed? And so this constant speed, yes, we know it's changing directions, but to get the magnitude, again, notice it says speed. We're going to go back to that circumference divided by period. And so 2 pi times the radius, which we already converted to 2,000 meters, divided by a period of 60 seconds. Again, I would convert to SI units from the very, very beginning. And so 2 pi, just FYI, you can use the pi button. You can do 3.14. Maybe you even know what 2 times 3.14 is. 6.28. So I'm going to say 6.28 times 2,000 and then divided by 60. And I get 209. And I'm already in SI units, so it would be meters per second. Well, now that we know this speed, and it's a constant speed, so it doesn't matter where it is, what is the magnitude of acceleration, centripetal? And so that's similar, plug and chug. Now that we know the speed, we can take that 209, square it, and divide it by the radius, which again is 2,000. And so that number squared divided by 2,000. And I get 22 meters per second squared. Math not too bad, I hope. Okay, now to forces. So again, the question's going to read like it does here. What is, oh, sorry. Next, save that for part D. Part C says, well, now that you know the centripetal acceleration, what is your centripetal force? So if we use Newton's second law, notice there's a net there. So net force equals ma. Well, hold on. If we know the centripetal acceleration, now mass is mass. It's scalar. There is no direction at all. Mass is mass. You got it or you don't, right? Then, if we calculate with centripetal acceleration, you're going to be calculating a net centripetal force. And so, we know that centripetal acceleration, we just calculated, it's going to be that 22 meters per second squared. The mass up above is 1,000 kilograms. And so we get 22,000. And what's a kilogram times a meter per second squared? A little review time. It's a Newton. Remember, that's what's equivalent to a Newton. Good deal? Now, I'll be honest, most times you're not going to calculate centripetal force this way. I mean, you will, but you won't. Centripetal force is not something I can just come over and centripetal you, right? There's got to be a string. There's got to be a frictional force. There's got to be a source. And so that's the next question. What is the source of the centripetal net force? In other words, without this force, the object does not make the circle. So again, this is a car on a circular track. We assumed it's going to be a horizontal track. And so just like me walking around in a circle, without this force, we would not make the circle. What's the source? Friction. Friction would be our answer there. And it's maybe a little easier to see when we draw the force diagrams, okay? And so that's what the next part is. Notice we've got two pictures. This top one is going to be a side view. And the second one is a top view, also known as a bird's eye view. And so get ready for both. Sometimes they'll even show you both. And so a side view is pretty much what we're used to. And so yes, there's a gravitational force acting on the car. It's on a road, a surface. Who remembers the surface force? Normal, and so it's perpendicular to the surface. It's a horizontal road, right? So a vertical normal force. And it's moving forward, yes, but something is making it go in a circle. And so that center-seeking acceleration happens because of a center-seeking frictional force. Okay? And I'm going to walk again in a circle and show you how it's towards the center. And so here I am walking forward, right? If I were to go this way, I have to push on the ground that way, right? We don't do this intentionally. We do it without thinking. But I'm going to push outward on the ground, and the ground is going to push me towards the center. Now it looks like I'm hobbling. I'm doing a slow step, right? That out foot, technically it's both feet if I walk normal, okay? I'm pushing away on the ground, and the ground pushes back on me towards the center, okay? If it didn't, we would not make the circle, okay? So Newton's third law, I push on the ground pushes on me. So we still got Newton's third law at play, but that's why the friction is center seeking. Everybody good there? Now maybe you're thinking, but there's 4 tires. Yes, so we're looking at the object as a whole. It's called as a point mass, the center of mass. But yeah, there's friction with all 4 tires that collectively have a sum of this frictional force on the object. What about a top view? Can we draw gravity when we look down on it? Not so easily, right? Because it's going away from us into the page. And by the way, that is a real direction in physics, but it's not in AP Physics 1. We don't go into the 3rd dimension, the z-axis. But yeah, you could note it, but typically you just ignore it. Normal force would be like coming at you. The arrow's pointing at your face if you're looking at the top down. But you'd still see the frictional force. Okay? And so we'll just say that FG and FN are in the 3rd dimension, which I'm just going to say is harder to draw. But notice your center-seeking force shows up on both, as it should. Good deal? Okay, let's do a little bit more. Page 3. We've got a revolving ball, and it has a hint here, it's horizontal. Estimate the force a person must exert on a string. So that sounds like an applied force on a string, but the string is gonna act on the ball. So really we're solving for the tension force here. Attached to a 0.15 kilogram ball to make the ball revolve in a horizontal circle, a radius of 0.6 meters. So no SI units to convert, those are all good. The ball makes 2 revolutions per second. And they go ahead and tell us, again, it's an early problem, so period is 0.5 seconds. So 2 complete circles in 1 second, that means 1 complete circle is half a second, yes? Okay. And so we want this tension force. Well, maybe you want to see the tension force. So maybe we draw a force diagram. Now, again, I'm going to draw a side view and a top view. And so side view is going to look a little different because it's a 3-dimensional horizontal circle. And that kind of looks like an ellipse to us. Now, I'll be honest, when you draw these horizontal side view, you want to stay on the left or right. That's going to be the nicest thing to do. And so there's our string, there's our ball. What forces are acting on this ball? Well, it has mass. We're not in outer space, so gravity is going to act down towards the center of the earth. It's a vertical force, right? Hint, hint, it's a horizontal circle. What other forces act on the ball? And by the way, our hand is somewhere holding the string. I'm not even going to attempt to draw a hand, so I'm just going to write the word hand. We're holding it, and y'all saw me demonstrate that earlier. I'm holding one end of the string, the ball's on the other end, moving in a circle. So I try not to move my hand in a circle itself. And so what other forces are acting on the ball? Tension. And if it's a horizontal circle, then the tension is actually going to act what direction at this point? Horizontally, center seeking. If the ball's on the left side, tension's going to pull it to the right in that moment. And so FT. Now what about a top view? So a top view of this, so if you're on the second story watching somebody spin a ball in a horizontal circle, it's going to look like a circle, okay? I'm going to keep the ball on the left side for consistency. Now what forces would be drawn on the ball as it moves in a circle? You kind of pause the, slow motion footage, you pause when it's on the left side. What forces would we draw? Well, gravity is kind of hard to draw now, right? Because it's a top view. I'm looking down and gravity is acting away from you in that 3rd dimension. It's harder to draw. So we just don't draw it. But tension, you can still parallel to the string. So we still have tension towards the center of the circle. And that's what they have in common. Y'all, that's the biggest clue. If it's a horizontal circle, your net centripetal force statement that we're about to write is going to be a horizontal statement. Gravity's there, it's just not contributing to the circular motion. Yes? Okay. And so now go back to step 1, diagram, check. Step 2, define the positive direction. Maybe we should do that first, right? And so positive direction, luckily, with circular motion, is what it is. What's our positive direction? Towards the center. And notice the tension force is towards the center in both pictures. So it doesn't really matter which picture, you should get the same. Now, gravity on the side view is not the 180. It's not necessarily center opposing. It's tangent to the circle, okay? It's 90 degrees. And so that would be a separate statement. That's not going to be in our net centripetal. We want center seeking, positive. And then 180 degrees, center opposing, would be negative, okay? And so next step is our F-net statement. F-net C, so I'm going to sum the forces that contribute to circular motion. Now this one's easy. The only one is tension. And that's what we're looking for, okay? And so that's what we're solving for. Now, I know the words say, must a person exert. I'm the one pulling on the string, but the string is the one pulling on the ball. They gave me the mass of the ball, the radius of the ball from the center. And so we're taking a ball approach, but because of Newton's third law, I pull on the string pulls on me, and the string pulls on the ball. And so Newton's second law says F net equals ma. But now it's not a linear acceleration, it's a centripetal acceleration. And we could take it one step further. AC, what we spent the first 15, 20 minutes with, AC we can plug in that tangent velocity squared over R. And we get mv squared over r equals the tension. Do not memorize this because tomorrow, maybe there's another force, okay? All right, so we're trying to solve for the tension. Do we know the mass? Yes, 0.15 kilogram. Velocity, did they give me the meters per second? No, but they gave me the radius, which means I can find the circumference, and they did give me the period. And so maybe we have to come over to the side to find that velocity, speed really, right? And so 2 pi times the radius of 0.6 divided by the period, 0.5. And so again, that 6.28 times 0.6 divided by 0.5, I get a velocity 7.54. And so now I can plug that into my force statement, and don't forget to square. Make sure I square it. And then divided by that radius, which again was given, 0.6. And so I take that answer squared times 0.15 divided by 0.6, and I get a tension force of 14.2, and it should come out newtons. Good deal? Now, who can find bad physics in this problem? There's an assumption we made, and AP will still make this assumption. They'll add clarifiers. Not air resistance. I told you gravity didn't contribute to the circle, right? It was a horizontal circle, but gravity is a vertical force. In real life, can this ball sustain a horizontal circle and not fall down because of gravity? No. Let me do my circle again. Again, I'm going to double loop it so it won't come off. Okay, so I'm going to try. So if I don't have a large velocity, notice I have a horizontal circle, but does this look like the picture we drew? I see an angle, don't you? This is our tetherball coming next class, where we actually don't ignore the angle. Now I can spin it more and more and more and try to get it horizontal, but if it has no vertical motion, doesn't it have some kind of equal and opposite force to balance out gravity? So in real life, you don't get this truly horizontal unless you put it, they put tables, frictionless tables to kind of support the gravitational force. But at the end of the day, you've got to have some other force balance out gravity or else it's moving down, right? And so technically tension should be at an angle. You're going to have components, and that's coming next time, okay? So this is those ideal, we made assumptions, okay? So just note to self here, maybe we say, we assume small angle. And if AP uses those verbiage, the small angle, and they don't give you the angle, then you're doing small angle approximation. You're just assuming you don't have to consider components. Okay, let's do this last question. Hopefully we have time to at least get a couple. Kind of going back to those proportions, still ball on a string, horizontal circle. It says you swing a ball with uniform circular motion, constant speed, in a horizontal circle on a frictionless surface. So this is what I told you, how they get rid of the angle. You've got a tabletop. So if I drilled a hole in this table and hooked a motor to it, and I was able to get it moving in a horizontal circle, normal force is supporting the gravitational force, but not contributing to the circular motion. So it says with a constant force, what happens if that force is reduced to 1/2? And so it doesn't really tell us here. I think, what do we, should have looked at this first. It says force, what happens? We could answer this from a speed point of view because they're changing the force. Or we could answer it if you assume, I'm going to take a speed approach. Okay. I'm going to take a speed approach. So we'll assume it's a constant radius. Okay, so the same picture as before, horizontal circle. Now we have a force that's changing. And so I'm going to go in and write this. So if mass and radius are constant, maybe I need to assume that. So mass and radius are constant. If my force is reduced to 1/2, notice force is proportional, not just to V, but V squared, right? And so to answer this question, I would say half the force means that I would have half V squared. If M and R stay the same, factor of 1, right? Well, but that doesn't really answer the speed. How would we figure out how the speed varies? Well, this is V squared, so I have to take the square root. What's the square root of 1/2? Square root of 1/2? I don't remember the exact decimal. 0.7. So I don't know what that is in fraction form, but the square root of 1/2 or 0.7. So if this is 0.5 V squared, your V would be 0.7. Okay. But at the end of the day, a smaller net force would mean you have a smaller speed, assuming constant radius. What happens if you double the force? So we'll go with the same approach. And so what happens to the speed? And so if you double the force, but have the same M and R, what happens to your speed? If you double the force, then you double V squared, right? To keep the equality. But what happens to V? So you'd have to square root 2, or I think this one is 1.4. Is that right? Yeah. So you still get a smaller V if the original is 1. A lot of times we say the originals are 1 when we play the proportion game. And then the last question, what happens if you keep force F? So now we have a constant F, but the velocity is increased. I think that should say radius to 4r. And so now we keep the same. So same F, same mass, but now we have 4r. And so notice, numerator, denominator, we want to equal the same force. What has to happen to v squared? If you have 4r, you're going to have 4v squared to maintain the equality. And then what with this one you can do in your head? What would happen to v? Square root of 4 is 2. So playing the proportion game, look at what's constant, what's not. I know this one wasn't really clear, so we did it together. Good deal? All right, next time we'll do some circular balls on a string. We'll put some outer space. I don't know if we'll be able to do them all, but cars on a hill, cars on a roller coaster, and hopefully we get to that angle appreciation with tether balls. All right?